Big news! Stuff is made from atoms. Okay, maybe it wasn't that groundbreaking, but what are atoms? Atoms are the building blocks of matter. Just like you take Legos and you combine different kinds in different proportions to make an airplane, you do the same thing with atoms to make things like Legos, toilet paper, books, random Tupperware lids, air, humans, and all other matter you can possibly think of or observe. Sometimes we think of atoms as little circles or little spheres, but that's not actually what they look like, though it is useful when we're trying to think of things like molecules and how those different atoms fit together. And sometimes we even make little models that have sticks on them to show the bonds between the different atoms. Atoms are small. It's hard to imagine how small they are. To give you an idea, if you took one human hair and you cut it in half and just looked straight at it and looked across the diameter of that hair, there'd be about 1 million atoms across there. Atoms of carbon. Carbon-12, that is, in case you're curious, which we'll talk about in a second. Trillions of atoms would fit in the period at the end of a sentence. A lot of chemistry is learning rules and then learning there are exceptions to those rules, and then learning that it's even more complicated than you originally thought. So when I say there are 3 subatomic particles, a lot of students say, what about quarks? And muons? And positrons? And strange quarks? But you already said quark. That's like saying what about trees and what about pine trees? And gluons? Okay, calm down. We'll talk about quantum physics in a different video. So, for now, there are 3 subatomic particles: protons, neutrons, and electrons. Protons have a positive charge. They're in the nucleus. Neutrons are neutral. They have no charge at all. Electrons have a negative charge. The charge of the electron is equal to the charge of the proton, but they're not equal in size at all. Protons and neutrons are about the same size. Electrons are super tiny. To give you an idea of how super tiny these are, a proton would have a mass of about 1.67 times 10 to the negative 24th grams. Since that's ridiculously small, chemists came up with a new unit called the atomic mass unit, or AMU. A proton and a neutron each have a mass of 1 AMU. An electron has a mass of about 0.000548858 AMU, and about 1,823 electrons would equal the mass of 1 proton. Protons are in the nucleus, and if you remember elementary school science, you probably remember like charges and magnets repelling each other. So if you have a bunch of positive things in the nucleus, how do you keep the atom from blowing apart? Because that's a nuclear reaction and that would be a problem. You have neutrons, which are neutral, and they act as a little bit of a buffer. Plus there's a force called the strong nuclear force, and it holds the nucleus of the atom together. Since electrons are negative, they're attracted to the protons, but they don't go into the nucleus. This is because they're flying around so fast. They're just going all kinds of over the place, all kinds of crazy, like a bunch of hyperactive mosquitoes that will never land in an unpredictable, scattered pattern. They're going so fast, they would fly off if they weren't also attracted to the nucleus. So it kind of balances out. So if an atom is neutral and doesn't have a charge, it'll have the same number of protons and electrons, and atoms like to be neutral. They want balance and stability in life, don't we all? When you look at a periodic table, you may notice that each element has a symbol, a whole number, and a decimal point number. Sometimes it'll also have the name of the element. The symbol is the element symbol. It's some kind of abbreviation. However, it's not always abbreviation you might think it is. B is for boron, that makes sense. But W is for tungsten, and AU is gold, and AG is silver. Some of these abbreviations come from Latin, so it doesn't always make sense. The letter you see is the chemical symbol, so whenever you write a chemical equation, you're going to use that letter, or 2 letters. It'll be 1 or 2 letters. These are just placeholder names. These elements have since been given names, but they're not naturally occurring, so we're ignoring those. So it'll have 1 or 2 letters. The first letter is always capital. The second letter is always lowercase, if there is one. See, this is a TL, not a TI. That is a capital I, so it can get confusing. And Cl, chlorine, that's a lowercase l. Al, aluminum. Sc, it's always the second letter is always a lowercase. The number on top is the atomic number. That's how many protons are in that element. The number of protons determines what element it is. So 1 proton, hydrogen. 2 protons, helium. 76 osmium. 82 lead. And on and on and on and on. So that's the atomic number. The decimal point number on the bottom is called the atomic mass. It's the average for that element. Every element will have an exact mass number, but sometimes the amount of neutrons can be more or less. Those are called isotopes. So if we average them all together, we get this decimal point number here. So 10.811 for boron, 12.0107 for carbon, so on and so forth. So that's just an average. But no one element is going to have that exact mass. So if we looked at carbon here, for example, it has 12.0107. Like I said, average. So most carbon is going to be called carbon 12. That means most carbon has exactly 12 things in the nucleus. Your atomic mass is how many things are in the nucleus total. That's protons plus neutrons. However, you may have heard of carbon 14. It's used to figure out how old dead things are, only if they're organic matter and only within a certain time period. But carbon 14 is a lot less common. Most carbon you will ever find will be carbon 12. Occasionally you get a few atoms of carbon 14. It's a little bit bigger, also less stable, but that's radioactivity for you. So if I added up all of the carbon 12s and all of the carbon 14s that we could possibly observe, and then I averaged them all out, then I would get 12.0107. But one atom will never have this decimal point number. Each atom has a specific number of neutrons. You don't have parts of neutrons in there. Each atom will have a whole number. It's just, these are called isotopes. A common abbreviation chemists do for different isotopes is they write the symbol, and then you can imagine that these parts are broken up into two little numbers. The top part will be what's called the mass number. So if it's carbon 12, there'll be a 12 up here. The bottom part is the atomic number, so it's always a 6. If you're doing the same thing for carbon 14, it would look like this. Atomic mass, atomic number. And make sure they're smaller. Both of them should be about the same height as the symbol. I'm not the best at it, but you know, I do what I can. Models are a very useful way to help us understand how atoms work, and we learn best by doing. So I'm going to make a model. I think I'll do a model of an oxygen atom. And I'm going to use marshmallows, Reese Puffs, sprinkles, and frosting. Now looking at oxygen, it has 8 protons. The atomic mass is 15.9994, so I would just round that to 16. We're going to make the most common isotope. So 16 and 8. Remember, once we round this to the nearest whole number, that tells us how many things are in the nucleus total. So there'll be 16 things in the nucleus, and 8 of them will be protons. Okay, I drew some rings on my plate, and I'll explain why in a second. What I'm going to do is I'm going to use marshmallows for my protons, cereal for my neutrons, sprinkles for my electrons, and frosting is going to be my strong nuclear force. The strong nuclear force is the force that holds the nucleus together. It's stronger than the force of repulsion between the different protons, and the neutrons help prevent the electromagnetic force from blowing it apart again. So what I'm going to do is I'm going to take a little dollop of strong nuclear force, and then I just use that strong nuclear force to add my protons and neutrons and build my nucleus. Now you can see I've made my nucleus here. Marshmallows are the protons, and they're kind of separated out by the cereal as much as possible. They would be closer to the same size, but I'm working with what I have here. Now it's hard to get this perfect, but they act as little buffers between them. Now I drew some rings here. The reason I did that is because electrons don't just hover around wherever, they're in specific energy levels. The lowest energy level will hold 2 electrons. So you can see kind of I have a ring here around there. The next will hold up to 8. This atom is neutral, so it's going to have the same number of electrons as it does protons. That means if 2 of them are here, only 6 are going to fit in the ring around it. It can fit up to 8 in bigger atoms, or in other cases, but it's not in this time. So I have 2 in my first ring and 6 in my second. So I have my neutrons acting as buffers between protons, and I have my electrons in specific energy levels. Like I said, 2 in the first, up to 8 in the second, but we only have 8 total, and there are 2 already in the first ring. You always start towards the middle and then move out. So you have 2 in the first, 6 in the second, total of 8 electrons. What would happen if I added 2 more neutrons? That would change the mass of the atom. It's no longer oxygen 16, it's now oxygen 18. There are now 18 things in the nucleus, so it's oxygen 18. Now what would happen if I added 2 more electrons? Because like I said, this row can fit up to 8. So now I have 8 in the outside and 2 in the inside, so all the rings are filled up. I have a total of 10 electrons. So now I have more negative things than I do positive things. My atom has a charge. When an atom has a charge, it's called an ion. That means I either took away electrons or I added electrons. The electrons do not match the number of protons. Protons are positive, electrons are negative. So since I have more negative things than I do positive things, my overall atom will have a -2 charge because I have 2 extra negative things. I have 8 positive things and 10 negative things. So therefore my atom will have a -2 charge. So my isotope that I made will be oxygen 18, or I would write it O818. That's the isotope I've created. Before, I was working with oxygen 16. When there were 16 things in the nucleus, it was oxygen 16. When there are 18 things in the nucleus, it's oxygen 18. And for it to be oxygen, it always has to have 8 protons. When an atom has a charge, we write the symbol and we write the charge up here. So if it has a charge of -2, we write 2 minus. So 2 negative. For some reason, chemists write it backwards. I don't know why. If we'd taken away an electron, which happens to sodium a lot, then it would have more positive than negative things, and it'd have a +1 charge. When there's just one, we don't write the number. We just write the symbol. So like chlorine, we'll just -1 charge, so we would just write a negative sign. But if it's more than one, we write the number and then the symbol. So we made an ion of oxygen. Understanding atoms helps us understand how the world works. The more we understand about atoms, the more we understand about how they interact with each other. The more we understand about that, the more we can understand how chemical reactions work and other processes in life. And that leads into things like biological systems, medicine, pollution, everything. Astronomy, salting roads, everything you can think of. Atoms are super important and they're super cool. That's really good stuff.